This is a movie perception test. Watch this brief silent.
This is an awareness test.
This is a movie perception test. Watch this brief silent.
This is an awareness test.
This is a movie perception test. Watch this brief silent.
This is an awareness test.
This is a movie perception test.
Clearly, somebody in this room murdered
this
Lord
brief
Smythe. Who?
This is an awareness test.
This is a movie perception test.
Clearly, somebody in this room murdered
this
Lord
brief
Smythe. Who?
This is an awareness.
Okay, let's get your attention. Everybody, welcome back. Today we'll be catching up on some theory lectures. We'll be finishing up perception, then we'll dive into data types, and then into marks and channels. Okay. Everybody, welcome back. Today we'll be I should close the Zoom window, the YouTube video. That's where the weird feedback came from. At least I know the microphone is working. Great. Before we do that, you saw that we posted a solution to homework 3. I was thinking about going through it. So this wasn't my fault. We posted a solution to homework 3, so take a look. If you have any questions, just post it under homework questions or come to any of the office hours. Homework 4 is out. Homework 4 should be mostly kind of the stuff that we covered last week about D3, and then of course we had a lab yesterday. Sorry the video isn't yet available, but I hope that we'll get it by the end of today. Homework 3, sorry. Jumping ahead. Well, any other questions, administrative or any otherwise, before we get started? So, okay, if not, then let's recall. We talked about perception. We talked about like pre-attentive processing or pop-out effects the last time. We talked about that, for example, hue, like a single hue pops out nicely. We did this little clap test. Everybody was very good at telling hue and size and like a different shape apart, but then conjunction targets didn't work. And then we talk about change and attention blindness. So basically, those are kind of just two variants of where we don't notice things that are going on in a scene because we're not actually paying attention to it, because it doesn't really, you know, all the changes are visible if we explicitly pay attention to them, but they tend to be overlooked. And I have one last video that I just wanted to kick off with here. So let's look at this.
At precisely 3:34 this afternoon, was brutally bludgeoned to death at London. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was posting grass last bedroom.
I was buffering his lordship's stone below stairs.
I was wandering like a Julia in the office there.
Constable, arrest. Julia Smythe. How would you know, madam, that any horticulturist will tell you under the top? It's just a matter of observation.
How good were you?
Clearly, somebody in this room murdered George Spy. Who? At precisely 3:34 this afternoon. But truthfully, bludgeoned to death. That's something. I want each of you to tell me your whereabouts and precisely the time that the dust is. I was buffering the George's stone downstairs.
I was watching my goodness. What is that?
Constable, arrest. Lady Smythe.
Okay, so another example for like paying attention in traffic, right? But also paying attention when we build data visualizations and when we build interactive systems. So the take-home points of this last part of the perception lecture is to find meaning in what we see, we must selectively pay attention to what is important. Like we really recognize things that we pay attention to, but we might miss a lot of other stuff. And the low-level vision we have is driven by object features rather than any conscious effort where to look. This is like this pre-attentive processing in the pop-out that I mentioned earlier. And attention is also like driven a lot by pre-existing knowledge, by expectations. For example, we expect, or we kind of expect people to speak, right? So we look at their faces and we might miss stuff that's around there. And the goals that we have stored in our long-term memory. And the final part of the perception lecture is Gestalt principle. And Gestalt principle is kind of like, was developed by a school of Vienna psychologists in 1923, Wertheimer and his colleagues. And they kind of like recognize these principles, but of course the research into why this is happening in the brain and so on is still ongoing and more recently. And so the idea behind Gestalt principles is that there are certain patterns that transcend the visual stimuli that produce them. So good examples for this are like, this is not, you don't perceive this as a segment, like a sequence of segments of lines, but you do perceive this as a circle, even if it's not a complete circle, right? You auto-complete this in your mind, similar with the rectangle. And so Kurt Kofka, one of the people in this Vienna School of Psychology, said, das Ganze ist etwas anderes als die Summe seiner Teile, which translates to like something that you wouldn't be expecting because you probably know the term a little bit differently. The whole is something else than the sum of its parts. You might know the more familiar idiom here that the whole is greater than the sum of the parts, but the original translation is more of like it's different, right? It's not greater, it's just different. And which is like a quote that is attributed to Aristoteles. And so these Gestalt effects, they can be very useful. For example, if you want to group features. So let's look at these. Like on the left here, you do perceive here columns of dots, right? You don't perceive this as a grid or as rows, you perceive this as columns. And that's because they have like reduced proximity between these items in these columns and increased proximity between the items next to it. And similarly here for the rows. And so if we if we have two elements, like if we have some examples here, like this we perceive as one group, right? They are all of equal proximity. This here we perceive as two groups. They're kind of like, you know, we have two separate groups that belong together. And this is just a demonstration that proximity is a stronger grouping principle than color, right? So that we do perceive those two groups that are spatially separated here as two groups, and we don't perceive orange versus black, right? We can consciously make an effort to recognize them as two groups, but it's not what we like intuitively do with grouping. And so, for example, in a UI design, you could kind of like just by varying the spacing lightly, you could kind of like distinguish between, do we have 4 columns or do we have 4 cards? All of this would be a possibility. And so you have to kind of like, when you do a layout, you have to play with this proximity. And so proximity is also grouping, linking by placing entities in close proximity. We can also group items by similarity. So we can group them by like essentially varying their appearance in a similar way. So for example, here we have all orange elements that makes a row, all brown elements that makes a row, and so on, right? And or a column in this case. Or here, all the dark brown elements, they make like a block here. So that works also with other things, with other channels that we can vary. And So for similarity, like here's another example that you could use to distinguish these groups, right? You could use just the color, and then clearly first it's one group, now it's 3 groups by using these color hues. We could also like use this similarity to focus on something, right? If we have 4 elements that look the same, then there's no focus element. But if we have one element that appears differently, this would be the focus element that people draw their attention to. Especially in this case, it's also bigger and more saturated, so people will pay attention to that. So similarity is useful. Like basically, what's going on is the co-modulation of a channel, such as color, shape, size, value, orientation, or texture. You can also add a glyph. You can add a label. You can frame, or you can add background, right? So these are all possible ways of like producing similarity. Remember that this like similarity really, like this is again an example that's related to this pop out. If we have these, if we use color here, this is very easy for us to perceive that those 2 items here are considered similar, but it's much more difficult for us to perceive that these 3 red items are similar, right? So these pop out properties, like again, really don't work so well if we have multiple colors or multiple stimuli of the same type, be it shapes or sizes and so on. And then the other thing is that I think I mentioned before, it's kind of like tricky to recognize those things in a cluttered environment. So here, like I'm showing you a Wikipedia page next to a Google Maps page, and there are 1, 2, 3, 4, 5 highlights here that are color coded, right? You might not spot one of them. This one of them here is in this picture here. So that's kind of like small, right? And it's kind of like not high contrast, so it's tricky to spot. So the size of the colored object is of course also relevant. And sometimes I find it tricky on, let's say, a colorful web page to use find in page to really see what is going on, right? And I'll show you some kind of like solutions to this problem a little bit later. The other thing that you could do is modulate everything else, right? This is kind of like what I think Windows 11 did this successively. When they had some security warning, they kind of grayed out everything else and gave you this like pop-up window that completely, you had to react to that, right? You didn't have any chance. They were basically doing this darkening everything else. You can also blur everything else. That also draws people's attention. It's a little bit more subtle, right? So you see those 2 points here that we care about. Everything else is blurred, but you know, that may work depending on the environment, or it may not work. And so here's some examples like the Microsoft Windows user account control that I just mentioned. But there's also studies on, like, you know, drawing people's attention in a dialog window to the most commonly used button, for example. So as you can see in this example here, or there's studies that highlight a class of items in a scatter plot, like here, by blurring all of the other elements, right? I just want to caution, blur, it's like one option to make things stand out, but it's not necessarily the best option. And blur is also binary. You can't blur a little bit and like expect people to notice the difference between a little blurred and very blurred. It's really just, is it blurred or not, right? So I'm gonna treat this again as a little experiment here. We have proximity, and think about which elements are grouped here. Then we have color. And I would have guessed that in the first example, everybody agreed that those 2 elements are grouped, and those 2 elements are grouped, and here those 2 are grouped, and those 2 are grouped. Then we have size. So everybody probably agrees that these are one group, these are one group, and then we have shapes. And everybody again agrees that this is one group and this is one group. And now we can do something to these charts to really change your perception completely, right? I can draw a line between them. And now, even though we had these fairly strong grouping principles before, we immediately recognize that those things that are connected are supposed to be grouped, right? Even if they're in another way different. And so this connectedness is this, and common region in a similar style is one of these Gestalt principles that simply, like, you know, tell us things belong to a group that are connected with each other or that are in a common region, right? And it does make a lot of sense intuitively. If I do something like this in outline, then I want to say something about those 2 elements, that they belong together in some way, right? That I want to highlight them and so on. And so you can surround items with an outline, a surface, or a volume, or a line or a curve. And so, like, we have this hierarchy essentially of features, right? So we have similarity, connection, and then enclosure, right? And so in the enclosure case, we'll probably understand that there's something complex going on, right? That we have two different groupings, and that maybe the enclosure is the strongest one in this case here. You can also, like, connectedness here, like this is like, well, maybe not the best example ever, but you know, you have points of a time series that you plot first with two different shapes, and they're kind of hard to perceive as a group, even though I use the same shape, right? If I do this as a line chart instead, it's super easy to perceive, right? And then if I want to highlight something, I can kind of like use this enclosure principle to highlight a particular point where those two lines, for example, intersect for the first time or where they reach their peak. So if we had like for user interface design, this would be like an example, right? If I just build like a frame around something, I have very strong grouping going on with that particular user interface. And connectedness is something that people have studied, like different ways, different designs. So for example, this is for set relationships. Think about, you know, highlight all the pizza restaurants and all the Indian restaurants and all the Chinese restaurants over a New York City map. And so there's 3 different versions here. The original paper back in 2011 did these kind of like hulls around them that kind of like look very interesting. And then here we have a continuous lines set, and then on the far right is what's called kelp diagram. These are branching lines, right? So these are all different ways of creating this connectedness, and they have different kind of like pros and cons. I think mostly, I guess you should also, if you're deciding between these, you might also consider factors as aesthetics, right? And as like what is easier to implement. So I think that this kelp diagrams, for example, is much easier to implement because you just connect points, right? Whereas this is also fairly easy to implement. You just connect points with a spline, but here you have to calculate some complicated fields, and you have to create a texture. And so even though I personally think this is the most beautiful one, it is really hard to do. So we can use Gestalt effects also for emergence of how objects appear to us. And these are like just some examples. So here, for example, we would assume that well, what would we assume? We would assume we see a circle that is occupied, or that like there is an rectangle on top of it, right? That's kind of like our assumption here. We assume continuity. We don't assume that the rectangle has any of those shapes, right? We don't assume that the circle, that it's like actually a Pac-Man, or that it has this little edge here, or that it has like a non-continuous shape, right? We assume continuity if we don't see it. And so we can use this continuity principle that kind of like makes patterns emerge, right? So like here we have scattered elements, and then we have continuing elements where we have 2 different curves. And so we do assume that things are smooth and continuous. And so, for example, if we have this setup here, we do assume that the 2 shapes that compose this are that, and they're not that. And that's kind of like also a reason for us to, for example, use continuous edges when we do network layouts, right? So if we do these discontinuous layouts here, it might be a little bit easier to avoid any kind of overlaps, or at least mathematically easier. But if we do these continuous routings here, it's kind of like easier to understand what's going on, even if we had some occlusion, right? And then this is like another example. I showed you the circle at the beginning. Here's just some other pictures, some more complex pictures where we do this kind of like automatically complete shapes, like the panda bear, the shoe. Those are actually not complete shapes, or all of the faces, right? We kind of like mentally run this closure and run this completion in our brains. And so here we even completely, like with very little stimulus about what the shapes are, we just see the edges, right? But everybody will perceive this as a rectangle, though we are not actually like showing much of the rectangle, right? We're showing maybe like 20% or less of the edges. And similarly, this here is this kind of like more complex shape that we can also perceive. Symmetry, we also perceive things to be symmetric, right? So in these 3 cases here, this one here we don't perceive like as one figure, but those here we perceive as a figure. And if similarly, if we have something like this here, this isn't a continuity principle, right? But we do assume that this element has symmetry. So we would always assume this to be like a cross, but not a shape like this, just because of symmetry. And we are also good at spotting where symmetry breaks down, right? So For example, if you want to have, if you have two very similar bar charts, series of bar charts, like for example, you've seen these demographic pyramids, like how long people live, right? On the left, you have males, on the right, you have females, and then you see the symmetry between them, how they're different. And it's very easy for us to spot these differences because they do break symmetry because women tend to live longer. And this is exactly this example, right? So here we see this asymmetry quickly up here, and then we see like different events that occurred in these people's lifetime, like the Great Famine. This is starting in 1917, and then in 2006 we see Civil War, Winter War, baby boomers, and so on. And so here's just like some MC Escher paintings, and to make it kind of like a little bit confusing, what is figure ground, right? Do you see the two faces here, or do you see the cup, or do you see the swans or the fish with some continuity? So you can take a look at them later if you're interested in this kind of stuff. So why do I tell you about those things? What are the applications in visualization? So let's go back to this example here. So if we want to search something, as I mentioned a few times, we can like do a simple color highlight, or we can do blurring, right? And so here I did the blurring, and it's really hard to see, right? Because this doesn't work all that well. There's these 5 same highlights. Like if you look very closely, you might see this word here is actually not blurred, but everything else is hard to perceive. Compared to like darkening the surroundings of everything else here, works fairly well, right? We see those different elements. It's fairly easy to spot for us the search terms. If we use color, it is okay, but we might actually miss the small ones that are like in not a very kind of like where the color is at the similar like saturated level as the background. We can make them blink. That is kind of annoying, but it works, right? It lets our attention really focus on them. Or we can do this, right? We can draw these connection lines on top of them. And so that's actually a research project I did back in 2011. It's like ages ago, where we looked at like, are these kinds of highlights effective? And we actually like developed a little, like one thing that gets a little bit annoying with these connection lines is that they tend to clutter stuff, right? So they tend to occupy something important. So there is, for example, some text in here that is being occluded. And so we developed an algorithm that does routing around this, right? So that takes in the saliency of the scenes and does kind of like some smooth routing around those scenes. And then we did like a perception study, and we saw that really people tended to not miss elements if we used highlighting like this, and they also tended to actually follow these visual links with their gaze, right? We did an eye tracking experiment back then for that. So this is called context preserving visual links. It's just a side note of how you can use this these kinds of principles here. So good. That you have to ask my colleague who made this figure 15 years ago. But yeah, it's not very, like, you know, in this case, it doesn't really make a ton of sense, the context here. So the takeaways here is knowing about perception is important for visualization and for UI design. You need to think about how to choose your colors, how to show relationships, how to draw attention to something that you want people to pay attention to, and how to minimize the risk of something being overlooked. And with that, I want to move over to the data lecture. Okay, so this is now like slightly drier subject, right? We won't be seeing any surprising things like attention videos or so. We'll be talking about different types of data. But it's very important for us to think about, because we need to be aware of the types of data when we want to make visualization decisions, right? So that really, like when we know the data types in detail, we can pick the right visualization technique. So it's really critical for us, everybody here, to understand what is going on, what is the data type, and then eventually what kinds of visualization can I choose for that. And so I'll be using 2 different terms today, or like I'll be distinguishing between data set types and data types. And so data set types are things like tables, networks, fields, or geometry. And data types are kind of the fundamental units, like items, attributes, links, positions, and grids. And so data set types are composed of data types. And then we'll also talk about low-level data types, like integers, ratios, ordinal, categorical, and so on. And those are still different from data types in programming, right? So we'll be looking at all of those different terms today. So the first thing that you have to know about data is your data set structured or is it unstructured? And if it's structured, you know the data types that are in your data set type, and you know the semantics about your data set, right? And so most of the data, probably all of the data that we'll be dealing with in this class is going to be structured, right? Like you have a network, you have a table, this table has headers, it has rows, it has labels, it has numbers, it has text, and so on. But all of this is neatly structured, and you can easily retrieve a particular value. However, in reality, data that we typically as humans consume is actually fairly unstructured. So we have no predefined data model for that. And that tends to be things like text-heavy data. For example, like me speaking here is like a form of data delivery, right? Or text on a website is unstructured data. It can be interspersed facts. It can contain times or dates or locations or numbers. It can also be video or images. All of these are unstructured data forms. And like a large, now definitely a large area of computer science is taking unstructured data and creating structure on top of it, right? This is what NLP, natural language processing, is about. This is what computer vision is about. Text mining is about. Object recognition, right? All of those things are about understanding unstructured data. And in data visualization, most of the time we want structured data before we start visualizing, right? We tend to not visualize unstructured data, but if we have unstructured data, we might use an NLP or a computer vision method first to extract structured data and then visualize that. Yes? So there's unstructured grids, but I would still put them into the bin of structured data here, right? Yes, I actually have a slide on unstructured grids. So there's always, like, ambiguity in terms. So here is an example of text visualization. So this is like a visualization of the King James Bible, and which is obviously unstructured, right? It's not that we have like a data set about, well, we probably have, but the Bible itself is not a structured data set. But then these guys, Frank van Ham and his colleagues, they did a simple algorithm to extract structure. And the only thing they looked for are a term like value or name X beget name Y, right? And that beget, for everybody who's not a native English speaker, means like essentially fathered, or is the father of or the mother of, right? So these are the like a parent-child relationship. And just by doing that, they were able to extract the structured information from the Bible. And so you see that here, like Abraham begat Isaac, begat Jacob, and so on. And they also ran this on like a different data set on 18th and 19th century novels, which is all about kind of like pirates and bootleggers and so on, right? And there they made an interesting observation. Here they looked at XS-Y relationship. And if we have two words here that I find interesting, we have the word wife, and then we have father's wife, officer's wife, ambassador's wife, apothecary's wife. And if we, on contrast, take bride, right, which has like a different connotation, we have freebooter's bride, bandit's bride, outlaw's bride, right? So we can learn a little bit about these associations by extracting the structured information and visualizing them like this. And we'll have a lecture on text and document visualization. We'll be diving into methods like this, but even into like methods for like looking at large text corpora and so on. Okay, so the next thing we have to think about is data semantics. Let's suppose I have a data vector here, Basel, 7, S, and pair. Like you might be able to guess what those things mean, but you can't be sure, right? So you need some semantics. And in a typical, like a typical data set, what we mean with semantics is the real world meaning. Is it like the name? Is it a city? Is it a fruit? Is it a height? Is it an age? Is it a day of month, right? Like something that's meaningful for us humans. we call this metadata as well, right? So the kind of like description of what's in the header of a table. Often there's like a shortcut in a data table, and then you have a data dictionary that explains this a little bit more, and so on. But all of this is essentially bringing in the semantics. And the most common example of semantics, at least for tabular data, is to have this in the header, right? So here we have our data vector that we had earlier, Basil 7 as pair, is actually a record in this table. The name here is Basil, 7 is the age, shirt size is S, and the favorite food is pear, right? Now this is like makes sense, right? Now we can understand what's going on, and now we can also pick maybe a reasonable visualization for that. Okay, let's talk a little bit about data types. These are the structural and mathematical interpretation of the data, and we distinguish between items, length, attributes, positions, and grids. And I want to note that these are different from the data types in programming, right? They, like, for example, an integer in programming can represent both an attribute or a length, right? So those are like there's no equivalency or so. It always depends on the interpretation. So what are items and attributes? So item is an individual entity, usually discrete. So for example, like a patient, a car, a stock, a city. And attributes are measured attributes about these items. They're observed, and there's some logged properties. So for a patient, it would be their height or their blood pressure at a certain time point. Or for a car, it would be the horsepower or the make. So these are the attributes about the items. And so in this example here, we have our items. These are the rows. The item here is a person. And then our attributes here are the name, the age, the shirt, the shirt size, and the favorite fruit. And we kind of like typically refer to like the intersection of like the attributes and the items here as the cells. Other data types are links. Links express relationships between two items. So like a traditional example is friendships on Facebook, right? These are like these social networks, or interactions between proteins. But of course, you can create these links very flexibly. And then we have positions. This is for spatial data. The location in 2D, for example, on the Earth's surface, or in 3D, like in an MRI scan, pixels in a photo, voxels in an MRI scan, or latitude, longitude on a map. And then grids, we have the sampling strategy for continuous data. So for example, if we observe something like temperature in either a room or on the Earth or in like a combustion engine, we have to sample this in some way. And we can do this with grids. And the questions are like, how many voxels are there in an MRI scan, for example, or what are the positions of weather stations in the United States? Okay, so now let's look at these data set types. We have tables, networks, fields, and geometry. And let's start with tables. Like this is the simplest one. We have flat tables, like we have one item per row. Each column is an attribute. We have a unique key for a table. And that key is sometimes explicit, right? If we have like a unique identifier, or sometimes it's implicit. It's kind of like the position of the row, right? Both are possible as keys. And often, but not strictly always, do flat tables not have duplicates. And then we have multi-dimensional tables where we index based on multiple keys. So here's our flat table that we have. We have our item again, and then here we have our values. And then at the beginning here, we have an explicit ID. So that is kind of like the key here. So here we don't need the implicit row number, but we have an explicit key. We can also have multi-dimensional tables. So here in this table, we have two keys. So first we have a key for patients, and then we have a key for genes. And so this could be like a gene expression data set. And then we might have, for example, this gene expression data set calculated at multiple time points or for multiple tissue types, right? Or we could have collected multiple items. And so then we have to first pick the dataset type or the time point, then the index of the patient, and then the index of the gene name, right? And so we can construct these multidimensional tables. And we'll have actually 2 lectures on tabular data visualization. So what you see here on the left is like a parallel coordinates plot, which is like a multidimensional visualization that we'll be talking about. And then here on the right is a kind of like a tabular visualization that uses size and color encoding. So yeah, more on this in the lecture on tables and high dimensional data visualization. On top of all of this, we also have collections. So how we can group items. So first we have sets, and sets are kind of like, express a relationship. They're kind of like a little bit like links, but they're more of like hyper edges, right? So sets, for example, we could think of everybody here in this club who goes to the student life center in the gym is in one set, right? Everybody who likes to eat sushi is in another set, right? These are just like shared characteristics, and so we can define them as we want. And then lists are like, when we talk about tables, we tend to think of tables as ordered, but like a list specifically is ordered, and it can also allow duplicates. And then clusters are very similar to sets, but they tend to be more of like these things are similar. They tend to be a little bit more fuzzy than a set, right? A set is usually hard binary. It's in that set or outside of the set. A cluster is more of these things that are in that cluster have some shared relationship, and we think they belong together, but it's not like an observable characteristic that distinguishes them. And so here in this example, we have 3 clusters, but also consciously left some points here unassigned to make that point, right? That this isn't a hard assignment. The next data set type are graphs and networks. And those two terms are mostly equivalent, right? Like I might be using graph and I might be using network sometimes. A graph is a connection of items via links, and items can be like also in the network often called nodes. Examples are social networks, power grids, road networks, computer chips. Like there's tons and tons and tons of applications for networks, and they're like probably the second most important data set for abstract data visualization after tables. Special types of networks are trees. Trees are graphs with no cycles, and they often are rooted. Trees can be very useful because they allow us to hierarchically structure information. They're a super important data structure. But we can also like use trees for other purposes. We can there's special visualization techniques for trees. And so we'll be covering this in the visualizing graphs lecture. And so the 3 main types of network visualizations are node link diagrams, as you see on the left, adjacency matrices, as you see in the middle, and then implicit visualizations such as a tree map, which you see here on the right. And so there will be 2 lectures on visualizing graphs and networks. Then the next data set types are fields. And these are the attribute values associated with cells. The cells contain data from the continuous domain, such as like wind speed, temperature, pressure, or anything like that. These attributes here can either be measured, like in the case of temperature sensors that we have all over the country, but they can also be simulated, right? That doesn't matter. Either way is fine. And especially if it's measured, we have to worry about sampling and interpolation, right? And this is like a big field in its own, signal processing and statistics and so on. Here's an example of a field visualization showing you air quality on top of a map of the Western United States. And you can see that we had some, like this is from a few years ago, there were some like major wildfires in Oregon, and you can see that kind of like the Portland region here has terrible air quality, whereas Salt Lake City, for example, wasn't quite as impacted. For fields, as I mentioned, we have different ways of collecting the data, right? So the simplest way would be a uniform grid, where we have kind of like exactly every like unit distance, we have like a sampling in all directions, right? So this is kind of like the case where we have the geometry and the topology completely like easily defined. We don't have to store a grid. We can just assume there is something at coordinates 2, 2, right? A rectilinear grid would be this example here, where we have non-uniform sampling, right? So for example, if we had an MRI data set, we could probably like throw away some of the stuff that's like outside of the tissue that we're looking for. Then we could have structured grids, for example, like a curvilinear grid. So here we have some structure, but it's not trivial like a uniform or a rectilinear grid. And then we have an unstructured grid, which you mentioned before, where we essentially have full flexibility. And this is like often what we use, for example, if we have like, if you collect data in some convenience way. But here we have to store both the position and the connection of the nodes in that grid. So this fields visualization and grid visualization isn't really a core topic for this lecture. If you're super into this, you should also attend the visualization for scientific data, which is like offered in the spring semester always. And we'll be talking a little bit about maps. And so we'll be looking, for example, at the wind map like this. But a topic like an MRI scan here and how we reveal bones versus other tissue types and so on, that would be the topic of this visualization for scientific data lecture. At this point, I want to make a little bit of a side note. Since this is a graduate class, I can talk a little bit about academic trenches as well. In academia, in the visualization community, traditionally there were three kind of subfields. There's like the information visualization, which is maybe what this class is mostly about. This is about abstract data, tables, graphs, and maps. The kind of thing that makes this information visualization an interesting topic is you're kind of free to choose all of your designs and layouts, right? And so it's a very creative thing. It's about designing, about coming up with something else, because it's like we don't, like there's no inherent good representation for a table, right? Or for a network. We have to come up with a representation for it. And there's also perception research happening in information visualization, right? Like what's the just noticeable difference between two colors would be like an InfoVis research topic. Then we have visual analytics, which is this kind of like funding-driven term that is InfoVis plus statistics plus machine learning, which tends to be fairly applied, which tends to be about systems. And so that's kind of like in the middle here. And then on the far right, we have scientific viz, which is all about spatial data, the fields here. And the characteristics of scientific visualization is that typically you're not free to choose your spatial layout, right? You have the spatial data like an MRI scan, and you have to find the best way to depict this reality, right? Like what is kind of like a good ray tracing function? What is a good sampling function? What is a good storage and so on for that particular field or data set? And one simple thing to kind of like decide when you're unsure whether a visualization is InfoVis or scientific visualization is, look at the background. If the background of the figure is white, it's InfoVis. If it's black, it's SciVis. Of course, this is jokingly, but it does apply in many cases. Okay, and then the last data set type is geometry. This is about the shape of the items, explicit spatial positions, points, lines, curves, surfaces, regions, volumes. We will like see a little bit of this when we work with maps. For example, we'll have a lecture on D3 maps on Thursday, and there will be like a dedicated lecture on maps later in the semester. But mostly this is a topic of computer graphics and CAD. And so it's not a core viz topics, and there's also other courses at the EU that go into this kind of data. Great. So then let's talk a little bit about attribute types. So here, like why I want you to think about attribute types is what are the classes of values and measurements that are out there. So I'm sure you all have like an intuitive sense about this, that there's a difference between a categorical variable, right, and a numerical variable. And so a categorical variable is also called nominal variable. So those two terms are mostly interchangeable. They are things like where you want to compare equality, right? So fruit, I don't know whether I should list gender here at this point, but fruit, movie genres, file types, and so on. Then we have another data type that is somewhere between categorical and quantitative. That would be ordered, and that is like often called ordinal. And so this would be like greater or less than something else. So for example, a shirt size doesn't tell you anything by itself all that much, right? But it, like, you know that a large shirt is bigger than a small shirt. Or a ranking doesn't make like a statement about how much better something is than something else. It just tells you that in this ranking, this one comes first, right? Or car classes, is it an SUV or is it a sedan, right? Those are in some sense, they're ordered right by their size. And then finally at the bottom, we have quantitative attributes where we can do math, like arithmetic. These are things like the length, the weight, the count, or the temperature. And for quantitative data, we can make a little bit of a distinction. So there's two data types. Here's interval and ratio data. And the key thing to distinguish is there a 0 point, a meaningful 0 point, right? And so my favorite example here is temperature. Like, who is more familiar with Celsius system than Fahrenheit here? few people. Okay, so for you, 0 has a meaning, right? It's the point where water freezes, which is kind of like meaningful for our lives because it might be slippery out there. For like in Fahrenheit, it's a different 0 point, right? So the Fahrenheit 0 point is like, the rumor has it that this was just like the Fahrenheit was a person, right? He defined this color scale, and then the coldest day back in England, he said this is 0, and that's why it's 0, right? So there's not a meaningful value here for 0. So you can't say that 0 degree Fahrenheit, or let's say 5 degree Fahrenheit is twice as cold as 10 degrees Fahrenheit, right? That doesn't make sense. So we can't do multiplication here. We can compare differences or intervals, and that's why this is called the interval range. But we can't like make these multiplications about it. Similarly, like the year is an interval date, right? We have like the year 0 exists, like a temperature 0 exists in Kelvin, right? But it's not this. We don't use it on this measurement scale. That well, it would be really hard with an actual year 0. And the contrast to that is ratio data types, where here the relative magnitudes of scores and the differences between them matter. And the most important part is the position of 0 is fixed, right? Like if I measure 100-meter race times, 0 is meaningful, right? Like I know exactly that somebody who took 20 seconds to run 100 meters was twice as slow than somebody who ran 10 seconds, right? So that the 0 here means that there's nothing of the measured entity observed. So if I have, like, for example, 0 liters of water, then I have no water. And it's not some kind of arbitrary like scale here. So that would be things like length, mass, age, weight, speed. And here we can measure ratios and proportions. So here's kind of like a summary, also something that I've asked in the exam in the past. What are the operations that are supported by these different data types? So for nominal data types, such as categories and also labels, we can just test for equality, right? Are two things the same thing? Is like the continent associated with a country the same or not, right? For ordinal data types, we can measure equality, but we can also measure smaller than or larger than. For interval data type, where we have the location of the 0 is arbitrary, we can measure equality, we can compare the size, and we can do like additions and subtractions, right? And for ratio, where we have 0 fixed, we can do all of our operations that we are familiar with. We can test equality, when we can make comparisons, we can do addition, subtraction, and we can do multiplication and division on these. So here's a little quiz. What types of variables, nominal, ordinal, interval, or ratio, are the following? 50-meter race time. I hear ratio. Everybody agree? Great. The college major. Nominal. IQ score. Ordinal. I would argue it's interval. It's a number, right? But it doesn't have a fixed 0 point, right? Like, for example, my cat would score 0 on an IQ test, but I would still say she has not 0 IQ. But yeah, so like there's like, there's a difference between 110 that is similar to the difference between 110 and 120. So we can do addition and subtraction, but we don't have like a 0 point. So that's an interval example. The car type here, SUV, sedan, wagon, truck, nominal. We could maybe make an argument about ordinal, but I would agree with nominal for most cases, right? And the car model, Toyota Camry, Ford Escalade, nominal, correct. The other thing we could also think of here is label. So for example, like the key, right? It could be, this depends on the data. If I have a data set with like multiple Toyota Camrys in there, it would be a nominal label. But if I had like, the average lifespan of a car of that make, then it would be a nominal category, right? So the difference between label is it identifies a unique item, not expected to be duplicated in a table, whereas a nominal label is a category and you expect it to be duplicated. Okay, so we also have sequential and diverging data for like numerical data. So we could have like data that is homogeneous from minimum to maximum. For example, the number of people in a country, right? So it's either 0 or like 1.5 billion, right? And this is like makes sense to visualize this as like one homogeneous series. Diverging, we have two or multiple sequences that meet. So for example, elevation data. So above or below sea level is like something that we tend to think of as diverging scales, right? Because it really makes sense that we treat them separately, because the one is kind of flooded with water, the other one is air. Or the temperature of water, we could think of below or above freezing or boiling, right? And this could be like actually for water, we could have like, or for kind of like temperature of anything, we could always have like a 3-part scale, like it's solid, it's liquid, or it's a gas, right? So that could be like our scale that we use for any kind of like element. And so who can spot something in this chart here or in this visualization? It's a map, and it's a map of a part of the US, but I'm plotting elevation on a continuous scale here, which isn't smart, right? But I'm plotting it on a diverging scale. You can very quickly spot it, right? It's Florida. And obviously, the upper scale is stupid. But just to make the point, right, that a divergent scale here is really meaningful to us. Data also has other structure. So for example, a lot of data we have about people's behavior is cyclic. We have weekends, right? And we have seasonality in some sense over the year. And so here on the right, we have a spiral visualization. This is like respiratory disease cases. When are people going to the doctors to get treated for a respiratory disease? And in the first spiral on the left, there's a 25-day pattern. So that means the weekends don't align. But on the right here, we see like a weekly patterns. And then and what we see here is that very clearly do those, like Mondays is when people go to the doctors, because Saturdays and Sundays, doctors' offices tend to be closed, right? So I'll wait until Monday, then I go to this doctor. And this is actually like, you see this for birth, right? Like people like get a lot more children on Mondays than they do on Sundays because of planned procedures and so on, right? They get planned according to cycles that we have. And so if you have a data set like that, you always want to look at, is there any cycle in there? Like, I'm not saying this spiral is the best approach to do that, but it's like a neat idea that's worth considering. And there could be different cycles. So for example, here, this is log data about like a version of the WIS website from a while ago. And then here you see like the semester, and then the summer, nothing happens, right? And then the semester, and then something happened here over the summer. The details don't matter. But if I zoom out, I see a different cyclical pattern, right? And so here I see like a weekend pattern emerge fairly clearly even in this log file data that about course, like visits to the course website. Okay, so to recap, when we have a table like this, we call the row the item or the element or the variable. We call the column here the attribute, the dimension, or the feature. We call the header of the table here the semantics. Where are the keys in this table? Column A. Let's look very closely. Exactly. Here we have an implicit key, right? Because an order might actually contain, like the order ID, which is in column A, might contain multiple items that go into multiple boxes, right? And so we have duplicates here. And so the keys here would be like the row number. What are our attribute types for each of the columns? So let's look at the order ID first. What's the attribute type here in these categorical, ordinal, quantitative terms? Ordinal. Could be ordinal, could also be categorical, right? Probably it makes some sense that it's the sequence of how things were ordered, but it's hard to absolutely say that it's certainly ordered. Then our order date here. I heard ordinal, I heard something else from up there. Categorical. I would argue that a date is quantitative, right? It's interval, but it's still a quantitative variable. Then order priority here. Here, categorical. Any other opinions? Ordinal. Yeah, I would agree it's ordinal, right? It tells us a little bit about like how important is it? Is low priority versus urgent. Product container. Yeah, ordinal is probably reasonable here. We have small boxes, we have wrap bags, which are the smallest, maybe with a small pack and so on. It's a little bit tricky without knowing the details of the semantics, but probably ordinal. Product margin, quantitative, and ship date, quantitative. Okay, so as you can see, we need to think a little bit about it, right? And also notice really that the data types in programming languages don't really like correlate at all, right? So the order ID, which is categorical or ordinal, is an integer, right? Whereas maybe the date is stored as like hopefully as a data object, but could be stored as a string, but in reality it's quantitative. Yes. So product margin is clearly quantitative, right? It's like a percentage. Like how much am I making on it, right? So if I'm making 0 on it, it's like that's meaningful, right? Here, this is even a ratio data set. For the product container, it is kind of like a bit of a judgment call, right? Here you have to understand the context. It depends. Like you probably, like it probably doesn't matter all that much to you, but you know, if you want to do a visualization of like what's the proportion of containers that I'm using, it might still make sense to you to distinguish between a large box and a medium box and know that they're like next to each other, right? So for example, if I pick a color scale, I could pick like a shaded color scale where the biggest box gets the darkest color, the next biggest box gets a lighter color, the middle box gets like a medium color, and so on. And so that would allow, like if we have this ordinal relationship, if we can define that, it helps us make a choice about our visualization. It doesn't give an order. It gives an order if you really know it, right? Like if you were the person creating the spreadsheet, you can look at these boxes and you can see which one is bigger, right? And you can also maybe even think about like which one costs more to ship and so on, and which one fits more. So I think there is an actual order here. It might not be trivially deducted from that table here. Yes. Yes, but you can like you can count. So that's the difference between interval and ratio, right? Like you can count days that have passed and seconds that have passed, but you can't count a date. And so that's why that's because you don't have a 0 point, right? So that's exactly the difference between an interval and ratio, right? If you can't meaningfully count it, like I don't have 50, like I can't count 50 degrees Fahrenheit meaningfully, right? Then it's an interval scale. That's you can't count it because you don't have a 0 point, and so it really only matters in relation to something else, right? I can clearly say that October 23rd and October 26th is 3 days apart, right? I can do this math and I can like make these kinds of expression, but I can't say something else about, like, for example, like with a 0 point. Does that make sense? Say that again. Not from a common 0 point, but they have, well, there is no meaningful 0 point, but there's like an agreed upon 0 point, right? The year 0. So we have like a convention so we can deal with them. That is like, that's kind of like what makes an interval scale, right? We have a convention in Celsius that 0 is the temperature where water freezes, and Fahrenheit is where this day was really cold in England. That's the convention we use, that we can use numbers to express these values. But since the 0 point is arbitrary, we can't do things like counting with them, right? Unless we have a reference point that we care about, right? So we can count the days since that date. Exactly. Exactly. So we can make this relationship, but the date itself doesn't have like a meaningful 0 point here. Okay. Yeah, so this is kind of like also debatable, right? Probably the order ID is the sequential number, right? So like you could probably make a good argument that this would be ordinal. Categorical and ordinal is sometimes tricky, right? It depends a little bit on what you need. For like, you probably wouldn't visualize order ID in a meaningful way, and that's why this is categorical here. But you could also, like, if you care about the sequence of when things come in, order ID might be like ordinal, like you might treat it ordinal, that you can say order 35 came in before order 35, right? Yes, but yes. Yes. What I'm also saying is that whether something is which data type also depends a little bit often on like what you need from it, right? So you could treat order ID here as categorical, but if you want to ask a different question, you could also treat it as ordinal. Okay. So this was, yes, and then we have this data versus conceptual model. So a data model is a low-level description of the data. We can like run operations on it, like floats with plus and minuses and divisions and multiplications and so on. But a conceptual model is a mental constructions that includes the semantics and supports reasoning. So for example, your data could be like one-dimensional array of floats. The conceptual model here could be temperature. Your data could be a 3D vector of floats, and your conceptual model could be space, right? But it could also be something else, right? So there's this, like, what the data is and what we think about it. That's very important. And so we, just like an example to illustrate this, like here we have a data model, 32.5, 54.0, minus 17.3, from floats to using a conceptual model, temperature, to using like one of the data types that we define, like continuous to 4 significance digits, that will be quantitative. We could bin it into hot, warm, and cold, into ordinal, right? Or we could make it nominal, as like paper burned or didn't burn at this temperature, right? So like it really depends on our, like, what we want to do with the data, how we want to abstract it, and we can often like use kind of like a more abstract level on top of a more specific data model. Oh, it depends on the context, right? So for example, is it a day above 100 degrees Fahrenheit? Is something that we frequently count now in Utah, right? If you look at the Salt Lake City or the Utah National Weather Service office, they count the number of days above 100 degrees, right? And so they have like their own category that they build from like an interval data set temperature, that they say, these are the days, because we have more than 100 degrees, that's now we're treating them as a category as like these extreme days. And we're using this as a meaningful proxy. Yes. Great. And then, of course, in reality, things are complicated, right? We have combinations, we have derived data. So networks can have attributes, attributes can have hierarchies, data types, as we just talked about, can be transformed. And real life is complicated, and we'll see these compound data types frequently. When, like, for example, when you do your projects, you might encounter mostly compound data types. Okay, and now I'll move on to what I like to call the visualization alphabet. So this is about, like, now we've talked about data. But now I want to talk about how can we take this data and encode it. And so first, for this lecture, for the Markson channel, I would like everybody to read this paper here. Like, we're not going to get to the discussion today. And so next Thursday, like not this week, but next Thursday, I would like to spend 10 or 15 minutes to discuss this paper, and that's when I'll be wrapping up those slides. Also, this is one of the papers for all of the grad students in here that are in the 6,000 version of the course. There will be a question on this paper in the exam, right? That's kind of like what distinguishes the exam for grad students versus the exam for undergraduates. So read that paper. We'll be talking about this at the very end of this lecture. We won't be getting to it today, so you have like almost 2 weeks to read it. This is about crowdsourcing graphical perception. Great. And now I would like you all to think about how can I represent these two numbers, 4 and 8, and you can just shout it out and I'll draw. Yeah. Roman numerals, right? This is symbolic encoding. Other ideas? What's it? Another symbolic encoding. What's it? Tally marks, yes. 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3. Great.
FOR and EIGHT.
Some other symbolic encoding. Size, yes, like size of a bar. Okay, let's do this. Roughly twice as big, right? Shapes, circles. Okay. Six. Oh, too much. Ratios of circles, yes. So we make circle segments. Yeah, like a line, and then 4 and 8. Square and an octagon. Well, I'm drawing an octagon. Let's just, yeah, well. Okay. Okay, I'm not drawing an octopus. Other ideas? So one idea would be maybe to use like a hatching pattern, right? I could use, this is kind of like my best approximation of color saturation, for example, right? Or like hatching pattern, the density of a grain. Similar to this one here, we could just draw 2 dots, right? Other ideas? Two-D coordinates, I could draw a line essentially from like this.
You could also do 2 lines, one with a slope of 4, the other with a slope of 8.
Yes, I could do that, like a slope of 4, and like it's hard to say what is a slope of 8, but so yeah, so this is exactly what this is about, right? Like, what are the different ways we can encode 2 numbers? And there's like actually, this is like a good sample, but there's many, many more ways that we can actually, like, for example, I could have volume, I could have the frequency of blinking, things that I can't really draw in chalk. But it's all possible to do that. And so this is what these marks and channels are all about. Marks are this unit that represents an item or a link. For this lecture, mostly think of it as an item, but it also is a link. So for example, a bar here is a mark, right? And the channel is the change of the appearance based on an attribute. And that would be here in this example, the height, right? So we changed the channel to visualize the difference of these 2 items, but we identify each item by its mark, right? In this case, it's a little bit more complicated, right? Here, we would say probably this group is our mark, and the channel is the number of items. And similarly, this is our second group. That is the mark here. The group is the mark, and the channel here are the number of items, right? But generally this applies, and if you think about it, you can always find this what identifies an item and what is the channel that communicates the magnitude or the property. Okay, and for items we have these basic geometric elements like points or lines or areas that we can use. We can also use volume, but that's rarely used for like perceptual reasons in visualization. Like if you don't need volume, you don't use volume. And I'll talk more about why that is at some point later. And for the links, like relationships between items, we have these things that we learned about in the perception lecture, right? The containment and connection. That these are used to communicate the marks for the links. And then containment here can also be nested, right? So here is just an example where we have 3 levels of containment or more even nested on top of each other, right? So this is kind of like also flexible encoding. And then the channels, which are also called visual variables, they control the appearance proportional to or based on the attribute. So for example, for position here, like this tick here is kind of like encoded by its position relative to my starting point. Or a shape, like different shapes would kind of indicate that there's a different like object identity, right? Or different category. Similar, different color or different tilt. We had this example with the pie chart and with the slanted lines here, where we had the tilt. And then we have size, the length of a bar. For example, here, we didn't actually have any bubble sizes or anything like that, right? But that would be another option, right? I can have go out 2 circles and have the area encodes the color values, or the volume, or the length, and so on. This goes back, at least formally, this was described by a French cartographer, Jacques Bertin. He wrote this very influential book, Semiology of Graphics. And he kind of like developed these theoretical principles for these visual encodings. And this is like the table that he has in his book. It's in French, and I kind of like put the English terms here, and you will see that the table that we use nowadays is fairly similar to that. So we have position, size, value, texture, color, orientation, and shape. And then he has the different marks, points, lines, and areas, right? And so he described this. And then we kind of like, people have studied this a long time, and they've like, this is like a perennial question in visualization. Which of those is better than the other one? And usually the question is, yes, we can say this within certain kind of like constraints, but it's not an easy problem, right? Picking good visual variables. And so how can we use them? So for example, if we want to encode, like if you have a vector with 3 values, we use as mark, we use a line here for this bar chart. The channel here is the length of the bar, but it's also the position here at the top of the bar, right? Because like it's not just the length, because they're aligned at the bottom. So we have length and position here, and we're encoding 1 quantitative attribute for 3 values, so 3 items that are like using the line mark here. In this case, in the scatter plot, our mark here is the point, and the channel is the position in 2D, right? So like this point here has like this value for 1 coordinate, and this value here for the other coordinate. And so here, position is the channel, point is the mark, and then we could encode these 2 quantitative attributes. Now, we could add another attribute, right? We could add a categorical attribute, for example, by using color hue. And then we could add 1 more attribute, like a quantitative attribute, by adding size. And like that makes sense, right? But you can also tell very quickly that this works nicely in the simple chart here, but might not work in any scatter plot that you can imagine, right? So there's always this trade-off that we'll be talking about a lot. 1 word on redundant encodings. Here, this is like a triplicate encoding here. So actually, we're encoding by like these 4 values, we're encoding them by the length of the bar, by the position of the top edge, and also by the value of the bar, right? So like we use 3 channels to encode the same value. And this is kind of like, you know, reinforcing this, and can sometimes be a very effective strategy. So redundant encodings is something that you frequently see in well-designed charts. Here's a chart from like a local news station. Like, take a look for a second. What's wrong with this chart? A y-axis is really terrible, right? Like, clearly this is not a data visualization tool, but just a graphics tool. So we have the value 8, and about 17 is supposed to be about twice as much, and then 180 is supposed to be about twice as much as 17, and then 656 is like 1.5 times 180, so clearly no. So that's not a good bar chart. Like obviously, you should use your channels proportionally to the data that you're encoding. So that's like a very simple rule that you can remember. Types of channels, we have kind of 2 different types of channels. The one, and they kind of map nicely to our data types. We have ordinal and quantitative data on the left for the magnitude channels, where we can ask questions such as how much or which rank. And these are things like position, length, and saturation are well suited for that. And on the right, we have identity channels. This is like about what is it, right? And here we have channels such as shape, color, hue, and spatial region that are effective to communicate that. And so this is a figure from the textbook by Tamara Munzner, our mandatory reading for this course. And this is kind of like, you know, in this case, ordered, like split up by magnitude channels versus identity channels, and then ordered from like what many studies have shown to be the most to least effective in terms of just pure perception, right? So position on a common scale is something that we can very clearly distinguish. Position on an unaligned scale is a little bit trickier for us to distinguish. And then we go down length, tilt, area, depth, 3D position, color luminance, color saturation, curvature, and then at the very bottom, volume of an object, like 3D size. And on the identity channels, we have spatial region, which is kind of like tells you something about position, right? Spatial region and position are basically the same thing. But this is also like this proximity that I talked about in the perception lecture, right? If the things are in one group, you can move them to one region, and then it's as easy for us to interpret them to be part of one group. And so position essentially is king in visualization. It's always the most effective way to encode something. Where I place it, especially in 2D, we can very precisely perceive that. And then we can also use color hue, we could use motion, or we could use shape. And so we'll be looking at these in some more detail. But first, let's take a look at this chart here. This is like a New York Times visualization, and it's actually something that we'll be doing on the homework, something like this. Homework 6 will be like that. So what are the visual variables? Like first, what are the marks here? Like we have tax rates for companies. So each bubble here, well, I already said it, but the mark is the bubble. Each company here corresponds to one bubble. So the company is shown as a bubble, the mark is the bubble. And what are the visual variables or the channels are being used here? We have size, yes. Size, you probably haven't read this, but size is kind of like how big this company is, market capitalization, right? Others? Position, yes, the position here is the effective tax rate. So this is like the position in X. Yeah. Exactly. Color is also representing the executive tax rate, but in bins, right? So here we have kind of discretized that these are the like low paying and the high paying and the medium paying companies, right? Others, like what's Y axis? Density. It's a trick. The what? The number, yeah, the number of the companies that pay, but not precisely because we also have the size of the bubble, right? So yeah, in some ways, but you would probably say that a Y here is more of an artifact of the layout, right? So Y position isn't really used. It still gives us a sense of how many important companies, or maybe like how much of the economy is at a certain tax rate, right? So in that sense, like the overall gestalt of the object. But what this chart tells us that, well, actually, most of the economy is probably in this body of things here, right? And they pay somewhere between 10 and 40. And then there's some outliers that pay more than 60%. And then there are some outliers that pay somewhere between 0 and 10%. All right, so like that is what the Y-axis maybe tells us. Okay, great. And so before we go into the details, let's wrap it up for today. So Thursday, we'll have a maps lecture. I might continue a little bit with this. And then next Tuesday, I'll be traveling, but Max up there will be teaching a lecture on design. And then after that, I'll be back to this slide deck. Thanks, everyone.